Therefore, when the paths meet up at location D, the quantum possibilities combine, or interfere, in a manner that depends on how much slower the neutron travels in the upper path than it does in the lower path. This, in turn, depends on how high the particle climbs in the vertical direction along the A to C path. The researchers found that if they gradually tilted the whole apparatus counterclockwise, as shown by the curved arrow, so the neutron had to climb higher and higher to reach the C to D path, then the neutron beam was observed to switch gradually back and forth between the C sub 2 and C sub 3 detectors. This behavior is discussed here. Consider the apparatus with two different tilt angles and the quantum rulers for each case. The essential difference is that the scales on the rulers are different for portions of the two paths. The distance between tick marks is longer on the ruler for the neutron when traveling along the C to D path than when traveling on the A to B path, because it is traveling slower. Imagine that on the left side, the possible paths interfere such that the major tick marks line up with each other at location D, and the neutron has the highest probability to be detected at C sub 3. Imagine that on the right side, the possible paths interfere such that the major tick marks in the upper path line up with the minor tick marks in the lower path, and the neutron has the highest probability to be detected at C sub 2. As the tilt of the apparatus is increased further, detectors C sub 3 would again have the higher probability to register neutron detection, and so on. How rapidly the outcome switches back and forth between detectors as the tilt angle changes depends on the strength of gravity in the vicinity of the apparatus. Thus, this apparatus could be used to detect differences in gravity's strength by moving it from place to place and repeating the experiment at each location. How is this interferometer different from the one discussed in the previous chapter? The interferometer discussed at the end of the previous chapter is not influenced by gravity because, in that case, the two possible paths were in the same horizontal plane, that is, at the same height relative to gravity. These should therefore be understood as top views rather than side views. Is this apparatus a practical gravity sensor? No, it is not. A major drawback of the neutron apparatus is that it cannot be made easily portable. The source of neutrons was a radioactive uranium U-235 fuel rod in a nuclear reactor, which is not easily or safely transportable, to say the least. To be useful as a gravity sensor, the device needs to be portable so it can map the strength of gravity over some geographic area. Present-day quantum gravity sensors, or gravimeters, are based on atoms, not neutrons. Atoms have internal structure, namely electrons confined tightly within the space surrounding a nucleus. I explain in Chapter 13 how the quantum behavior of atoms leads to the technology of fantastically precise atomic clocks and gravimeters.